So we go to the second part. So the second part of our story, I already make like a preliminary thing, which is the burning platform. What is happening in reality? I mean, during anesthesia, pain doesn't exist. What exists is the surgical stress and the changes in the autonomous nervous system, what is called this surgical stress, is what is damaging the patient. Pain only exists, and we will see that later on, if the patient is awake. We can only perceive pain when we are awake. Who here has gone to sleep with a toothache, and when he gets asleep, suddenly the pain disappears? I understand, and it's very clear that it's very difficult to go to sleep when you have a toothache. But if you get asleep, then pain disappear. It doesn't mean that what it was provoking the pain disappear as well. What means is that your cortex is asleep, so you cannot perceive pain. But as well, obviously, there is all those processes in your body that are still going on, which is not pain, is surgical stress, we can say, or physiological stress in this case. So this is the reason why we have to measure the autonomous nervous system. And I would say that the best way to assess the autonomous nervous system is the heart rate variability. And this is something that was already said by a document of consensus of the cardiologists, US Association and European Association, saying that heart rate variability, and I will explain you now what heart rate variability is the best way to assess the autonomous nervous system. And as we said before, the autonomous nervous system is the system that is managing your life. Obviously, heart rate variability should be the fifth vital sign and not pain. So heart rate variability is a process that we think that appear. It's just an hypothesis. It's something that just appeared when we were living in the environments with very low oxygen. We were talking about energy, right? And where do we get the energy? We get the energy with oxygen and with glucose. We oxidate the glucose with oxygen in order to obtain ATP, which is a molecule where we store our energy, okay? So we need oxygen and we need glucose. And what happens if, because we are pluricellular individuals, so we need to have a pump that is expending energy to send the blood to those lungs that are gonna obtain that oxygen and send that to the rest of the organism. So that pump is consuming oxygen, right? It's consuming energy. What happens if the amount of oxygen that we are trying to get is not enough, even just to compensate the expenditure of that energy that my pump is doing? So I have to make a system that will just expend energy when I'm gonna be able to get oxygen and will not expend that energy when I'm not gonna get that energy. So this is what the autonomous nervous system is doing through two nuclei in the brain that you can see on the image here. You can see here, let me put this. So you can see the nucleo ambiguous and the nucleo accumbens in the brain that are managing when the heart is gonna beat and when the heart is gonna stop beating, not exactly, but a beating slower. And it's gonna depend if I have oxygen or I don't have oxygen in my lungs. So when I'm in inspiration, it means that I'm getting oxygen in my lungs. So my nucleo ambiguous will let the heart beat faster to send the blood to the lungs to recover, to gather all that oxygen to be sent to the rest of the organisms and the cells in order to make that oxidation of the glucose. But when I'm in expiration, obviously I'm not gathering more oxygen, so I have to decrease the amount of energy that I'm expending. So I'm gonna beat slower in this case. And that is gonna be driven by the nucleo accumbens. So if you see this, in fact, we can measure those distance between R to R, and we will be able to realize how those two nuclei are working. The solitary tract nuclei is really connected with the ambiguous and the accumbens. And this is one of the most important nuclei from the autonomous nervous system. And I put the pointer here because I want you to realize that our monitor is a brain monitor, because we are looking at what the autonomous nervous system is doing, managing by those two nuclei. So with our monitor, with the ANI monitor, we are going to assess the distance between R to R in order to see how these two nuclei are working. We have some baroreceptors on the terminal bronchus that are detecting stretch receptors that are detecting when that air is coming into the lung because they are expanding. So we detect that, and that information is going through a nerve that is called the vagus nerve. And it's the vagus because, do you remember, it's the parasympathetic. The parasympathetic is the rest system. That's why it's vagus. In Latin, vagus means lazy. Okay. And that information will go up into the ambiguous and the accumbens, and depending if he's detecting more pressure or less pressure, then they will send the signal to the sinus node in the auricula, in the heart, and will tell, hey, go faster. You've got oxygen in your lung, go slower, you don't have that. Okay? So what we are going to do then is to measure those distance between R to R. And those distance will decrease while I'm in inspiration because the beats will be faster, and in expiration they will go slower. So we are going to measure those distance between R to R. So probably you have thought that if someone has a heart rate of 60, it means that the distance between beat to beat is just 1 second, which is not the case. Normally those distance will increase over 1 second when I'm in expiration, and they will decrease when I'm in inspiration, will be below 1 second. So we can make that media and see the differences of that media 1 second if it's over or below. And we can draw a tachogram that I will show you later. So this way of analyzing the autonomous nervous system has been already validated by a document of consensus of the US Cardiology Association and the European Cardiology Association already in 1996. So it was a long time ago. And they already said that the high frequencies of that heart rate variability are directly related to parasympathetic activity. HF component, and we will see what it is directly related to parasympathetic. So as I was explaining to you, what we are going to do is to draw a tachogram measuring the distance between R to R that are going to decrease and increase, decrease and increase. As I'm in inspiration, they will decrease, and expiration, they will increase. Okay, they will increase in expiration, decrease in inspiration, etc. Decrease, increase, and we can draw this tachogram in which the distance in inspiration will be shorter and will be higher in expiration. This, in fact, is like the EEG of the nuclear accumbens and the nuclear ambiguous. It's like the EEG of the autonomous nervous system. And like all other EEG monitors, we can analyze it through different mathematical methods. So the mathematical methods that we choose is fast wavelet transform analysis. And this is very unique compared to other methods of analyzing heart rate variability. Heart rate variability was normally assessed by the cardiologist, okay? In fact, you know who started to measure heart rate variability? It was discovered in neonates, because they were seeing that those babies who were in the belly of the mom and were losing this chaos or this change in distances, they were having worst probabilities of survive to the birth. And those who have a higher variability, they were the ones who will survive. And later on, then the cardiologists were using that, and they were using holters. So they were putting to the patients a machine that is collecting the data of the ECG during 24 hours. And then they analyze that through a mathematical method that was called Fourier transform analysis. We don't use Fourier, we use fast wavelet transform, which is the difference between the two. Fourier transform analysis is meant to be used for stationary signals that doesn't change so often, or for signals that you collect for a long period of time. So the cardiologists were just collecting the 24 hours data, and they were analyzing off record. because we want to analyze it online, we need faster analyzing methods. And fast wave-left transform analysis is the one that is allowing us to do exactly the same thing that Fourier, but on real time. Okay. So fast wave-left transform, in fact, what it does is what the light, what the water do when the light goes through it. When it's raining and the light of the sun goes through the drops of the rain, you can see the rainbow, right? So you see, in fact, all the lights that are composing that white light. Huh? So we see all the frequencies. There are more frequencies, even the ultraviolets and infrareds, but we see the ones that we can see, which go from the red to the violet, right? We are going to do exactly the same thing with this wave. It's the same thing that, for instance, other monitors like SetLine is doing as well with the EEG signal, decomposing it into the different bands of frequency, the delta, the theta, the alpha, the beta. Huh? We are going to do the same with this signal of the autonomous nervous system, and we are going to see the spectrogram that is composing this autonomous nervous system EEG. And there are three kinds of frequencies. The ones that are very low frequencies, the ones that are low frequencies, and the ones that are high frequencies. They are on the higher frequency range. We have seen already that the high frequency range is directly related to parasympathetic. The LF, the low frequency, is directly related to sympathetic and baroreflex. What baroreflex means? Baroreflex means change in the volumes inside your body. We are nearly an 80% of water, and that water needs to be distributed all through the different parts of the body. And the autonomous nervous system is managing that thing as well with the sympathetic and parasympathetic. So that is expressed in this LF band. And this is very important because there are some parameters that are trying to use heart rate variability that are using LF to assess nociception, but a lot of times they are confounded by changes in volemia because that information is also well on the LF. This is the case of SPI. The VLF, the very low frequencies, is just related to the corticotrope axis, so to the release of hormones and as well temperature management. Okay? So the only band which is pure to parasympathetic is the HF. So we don't have any artifact, anything, if we look at the HF. So we're going to filter out that HF band. We are just going to collect the HF band. And in the normal way of processing, we could see which is the power of this band, for instance, or even we could have seen in the temporal analysis, not with the spectral analysis, which is the distance between R to R or other analysis. But what is going to be different as well comes here again. We are going to use that HF band and we are going to pass it again through fast wave transform on reverse. We are going to pass it again through the prisma and we are obtaining the wave that is corresponding to that HF band. And this is exactly the wave that we are showing to you in our ENI monitor, in our V1 and V2 monitor. As you can see with my arrow here, we've got the ECG with the yellow points over the R waves. This is very important because it's telling us that what we are detecting is the R wave all the time. This is why it's crucial to have the ECG. We have to see that. And then we offer you the wave of the HF band, okay? In a rectangle that goes from 0 to minus 0.1 plus 0.1 because it's normalized, okay? And from 0 to 64 seconds. This is because we are analyzing the HF band of an ECG of 64 seconds. Imagine that you have an ECG of paper. So we press the play button for 64 seconds. We cut that paper. We measure the distance between R to R. We do our tachogram of 64 seconds. We pass it through the prisma of fast wave transform. We obtain just the HF band. And we pass it again through fast wave transform on reverse. So we obtain now the wave of the HF band of those 64 seconds. So what we are going to do now, this is why we call it a graphical measure. We are a graphical measure. So what we are going to do now is to analyze the area under the curve of this. in another way, we could say, which is the percentage of occupancy of that green net? With just some training, you will be able to tell you directly, just looking at that, which is more or less the percentage of occupancy. Now, I would say that it's occupying like half of it, right? So it would be like a 57% of occupancy. So the ENI number is not exactly the amount of occupancy of just those 64 seconds. What we are going to do is just to press 1 second more. In this one is 57. We press 1 second more of the ECG. We get that 1 second more, and we put it with the 63 previous seconds. We made the same calculation and we obtain another number, for instance, 44. And do the same how many times? In fact, we do it nearly 1 minute time. In fact, is 56 seconds time. So we divide it by 56 and we obtain the media of those previous 56 seconds. And with the orange, we do it again another 56 seconds. So it's like 100, nearly 2 minutes. Okay. That's why we said that the yellow ENI is 1 minute delay and the orange ENI is 2 minute delay. Okay. But if we add those 64 seconds previous, we have to add another extra minute. Okay. So more or less, this is the delay of the yellow ENI and the orange ENI. The yellow ENI, it's a more rapid and more instantaneous index, will change more rapidly, but what will change very rapidly and instantaneously to the actions of the surgeons will be the green net. Okay, every second that change and is telling you what is happening in real time on that autonomous nervous system. So when the surgeon is going to start his incision, and if there is not enough analgesia on the patients, the first thing that you will see, even before the ENI dropping, you will see the green net getting narrow, because the distance between R2R are getting narrower, the variability is getting narrower, okay? And then you will see the yellow ENI, the instantaneous ENI, falling down because it's a media of 56 seconds. And then the other one, which is a much more stable index because it's much more promediated, will change. So the yellow ENI is the percentage of parasympathetic in the last minute, and the orange ENI is the percentage of parasympathetic in the last 2 minutes. This is very important because ENI is not a complex index, it's not a created index. ENI is a measure of the autonomous nervous system, the same measure than the amount of glucose that you have in your blood, or your age, or your weight, or your pulse oximetry. It's a real measure. If the ENI goes up, it means that the percentage of your parasympathetic system compared to the rest is going up. If your ENI is going down, it means that your percentage of parasympathetic is going down. Okay. Another very important value is here. It's called energy. Here it says 0.09. It's very low. The physiological values of energy goes from 0.05 to 2.4. But in an awake and healthy patient, those values will be between 0.9, 0.8 to 1.4 in an awake patient and healthy patient. If that patient is asleep, the anesthesia will blunt the amount of energy that you have, which means the amount of autonomous nervous system that you have. Do you remember that we said that autonomous nervous system is managing the energy? In a way, it's this thing, okay? So the bigger the energy is, the bigger the autonomous nervous system is. The smaller the energy is, the smaller the autonomous nervous system is. So, as I said, the energy values, physiological values, goes from 0.05 to 2.4, but in a healthy awake patient, you will have from 0.8 to 1.4, 1.5. In a frail patient awake, it will be 0.3, 0.4. In an anesthetized patient healthy, it will go to 0.3, 0.4. And in a frail patient, when I anesthetize him, it will go below 0.1. those patients, there are already articles, are very likely to have hypotensions due to the low amount of energy that they have. Okay, their autonomous nervous system is not able to cope easily with the stressors, so cannot really sustain that balance in your autonomous nervous system. In a way, I always compare it like the amount of money that you have in your bank, right? If you have a lot of money in your bank and you have a problem, then you will be able to solve it easily, right? If you don't have that money, then you are in a big problem. This is what happens with your energy, okay? And the ENI, in fact, is just the percentage of that energy that you are expending on the parasympathetic side, okay? Okay, so more or less, this is the screen of the monitor, and I'm realizing and emphasizing that we are a measure. We are giving you energy. His unit, it's milliseconds, and the ENI value doesn't have units because it's a percentage, okay? It's not the total amount of parasympathetic, but the percentage of parasympathetic, of the autonomous nervous system that is parasympathetic. I want to tell you as well that we are already being integrated in very different other monitoring companies like Massimo. In the root, we have the Mognine, and you can see the yellow ENI, the orange ENI, and you can see the energy value as well. We have as well a contract signed with Mindray, which that model will be released quite soon. And we've got as well some other OEM agreements with other companies like Atom and etc. And the energy, this is what I told you. The energy is the size of the cake that you have. It's the amount of money that you have in your bank. Okay. Our energy is not exactly what is called total power, and it's not exactly what is called the SDNN value. SDNN value is a temporal measure of the autonomous nervous system through the heart rate variability, and the total power is a spectral analysis. But it represents exactly the same thing. It's the total amount of the autonomous nervous system available to defend yourself against the threats that you're going to find. As I said, we are a measure, and here you have the confirmation. This is the comparison that we made in order to submit our monitor to the FDA. So our monitor is available in the US. We have FDA clearance, as many other monitors doesn't have, and we are directly related to HF-nu, to the high frequencies normalized. So basically, whatever you read regarding HF-nu, you can, obviously we have to demonstrate it as well with our monitor, but you can say or think or hypothesize that it will happen as well with ANI. Okay, so ANI is measuring the percentage of parasympathetic, and it's proven. So this is the way in which we are gonna take control of stress, in which we are gonna put the devil in the jail, right? Measuring the autonomous nervous system, and then using some kind of drugs or procedures in order to maintain my autonomous nervous system in balance. But we have to validate it, right? We're going to validate it. This is, we have nearly 160 publications already. But I would say that with just 2 publications that I'm gonna show you, you will be able to demonstrate that ENI is very useful. This was published in Anesthesiology in 2017 by a group of doctors in Germany. And what they are doing is basically very simple. They are just getting patients under propofol, and they are going to submit those patients to an electrical stimulation. So it's a fixed stimulus, a current that will provoke a fixed nociception stimulation, right? And we are going to see the relationship of different parameters that they said that they are measuring nociception to the change and to that stimulation. Okay, so we have this graph is what is called the rock curve. A rock curve represents how much is related one event to another. So the electrical stimulation to the change in the parameter. So we've got here different parameters. We've got the BIS monitor that we know is just hypnosis. We've got the heart rate and blood pressure in dotted orange and red dotted lines. Then you've got the green, which is SPI. Then you've got the red one is ENI, and the blue one is pupillometry. So we're going to make a tetanic stimulation with patients with propofol and intracutaneous stimulation, which is very similar to an incision with propofol as well. So when the curve goes much more on the left side, goes up, the area under the curve is much near to 1. It means that the relationship is very good. 1, it means that the relationship is perfect. It means that when I do this, I may say that, every time that something occurs, that other will occur as well. So the relation is perfect. And when you are here on the diagonal, the relationship is 50%, is 0.5. So you have the same chance of having the event than throwing a coin, okay? So the BIS monitor obviously is on 0.5 because BIS monitor is not looking at nociception, it's looking at hypnosis. So BIS monitor is not useful for detecting nociception. Heart rate and blood pressure is useful on 75% of the cases. There is 25% of the cases that is not useful when you're just under propofol. SPI is a little bit higher, nearly 0.8, 0.78. Then ENI 0.9998 and pupillometry 0.99, so very similar. And in the other way around, we are higher a little bit than pupillometry. So it seems that with propofol, pupillometry, and ENI are the best ones to detect the noxious stimulation. But when we add remifentanil, which is very obvious during surgery, normally you will add opioids or analgesics, right? You see that pupillometry is very much affected. They have a sailing effect. The pupil cannot dilate itself anymore. But look what happens with heart rate and blood pressure. It goes to 0.5. Doctors are using heart rate and blood pressure to titrate nociception and analgesics when the relationship is just 50%. Do you imagine the doctors flipping a coin and saying, okay, it's face, I'm going to add more fentanyl. It's cross, I'm not going to add it. Well, this is what they are doing when they are managing their analgesia with heart rate and blood pressure, when they are using opioids. 0.5, no relationship. And the biggest relationship is due to ENI monitor, which is 0.9. Okay, 90% of the times we are going to detect the noxious stimulus. We will answer all the questions later on when we finalize the presentation. So we've got an index, or I would say a measure, that is directly related to noxious stimulation. We have seen that on the FUNK study. How are we going to use it? Well, we created this scale. Well, in fact, we didn't create it. What we did was just to observe which were the thresholds that we have to maintain. And in this case, in order to avoid the hemodynamic response, we said, and you have heard a lot of times, that we have to maintain our ENI values between 50 and 70. Which is the reason for this? Well, the first study that was done and published was just comparing ENI to hemodynamic response, because hemodynamic response was like the gold standard for nociception. So we realized that the relationship, and you see the rock curve here, that the relationship between ENI and hemodynamics is 75% of the cases. It's not all the time, it's not 100%, which is good, because if we were just 100%, then they don't need ENI, obviously, right? Because we do the same thing that hemodynamics. No, there is 25% of the cases in which we were not related to, so we don't know who, hemodynamics or ourselves, were better to detect nociception. Now we know, because in the FUNK study we proved that, okay? We proved that we were better to hemodynamics. But here, that publication was 2017. This one is in 2010. So what we did here was to see which were the thresholds in which ENI will correlate to the hemodynamic reaction. And we saw that when you go below 50, the increase of hemodynamic reactions appears. And when you arrive to 30, there is a 100% of probabilities that you will have an hemodynamic reactivity. And when we are in 82, you never had a hemodynamic reactivity. This was done with opioids, with sulfentanyl. So we can say that if you maintain your ENI on 50, 70, you will not have a hemodynamic reaction and you will avoid overdosing. Okay? If you go below 50, your probabilities of having an hemodynamic reaction increase until you arrive to 30, in which there will be a 100%. Okay, so if you are on 45, it doesn't mean that you will have an hemodynamic reaction. It means that the probabilities that you will have it are higher than if you are on 60. Okay, and if you go to 30, then you will have for sure an hemodynamic reaction. And in this publication, we saw as well that the hemodynamic reaction occurs nearly 5 to 10 minutes after the ENI falls. So you can prevent the hemodynamic reactivity. Okay. So this is the reason why of that threshold, 50, 70. But I want to tell you as well that in a sleep patient, imagine that you're sleeping comfortable this night. Your ENI value will be 100. Your parasympathetic activity will be very high. Okay. It doesn't mean that you're overdosing, right? It means that your parasympathetic is very high. And that's not bad. It is bad if I am just giving opioids and I'm putting you on 100 just with opioids. Then you can have side effects because the amount of opioids that I have to give you to leave you to that point when you are under surgery is that much that you will have nausea and vomit, etc. All the side effects. Okay, but if you are just sleeping, you can go to 100 very easily, and there is not overdosing of everything. Okay, of anything. Another point, if you're under an epidural and you are asleep, the epidural will block completely all the afferences. So it's very likely that your ENI values will go over 80 and 90. And that is not overdosing. It means that your sympathetic is very good under control. Okay? And when you go with multimodal, which means I'm mixing different kinds of analgesics, like opioid-free anesthesia, for instance, I'm adding dexmedetomidine, lidocaine, ketamine, sulfate of magnesium, etc. Then it's very likely as well that I will have an ENI of 100. And I'm not going to have side effects because I'm adding just a little bit of every drug, which is provoking a very big block. And those very little things are not provoking side effects because it's very small amount, but will provoke all combined a big sympathetic block. And this is why it's very good. Okay, I hope you understand this. If not, I will clarify later on the answer and question and answers. So we go for the next part. The next part is Annie in the OR. As I told you, we have two values. We have the ENI value, which will help us to titrate and guide our analgesics. And we've got the energy value that will tell me what is happening with my autonomous nervous system and how powerful my autonomous nervous system is. And this is important, no? One of the main things that we have to understand is that we are not treating pain while I'm during general anesthesia. As I told you before, if I'm unconscious, I cannot feel pain. But what do I have? I have the reflex of my autonomous nervous system. And the reflex of the autonomous nervous system means the sympathetic activation and means the inflammation process activated. And that inflammation process is the one that is going to provoke that acute postoperative pain, the chronification of that pain later on, and as well in frail patients, we can talk about cancer and we can talk about cognitive dysfunction and other problems, infections, etc. This was said by Dr. Gray already in 1962. Probably you have heard about the triad of anesthesia, right? Hypnosis or narcosis, as he said, analgesia, and neuromuscular blockade agent. Those three arms, it's anesthesia. That was done by Dr. Gray in 1952. But 10 years later, he said he was wrong. He said analgesia doesn't exist during general anesthesia because a patient cannot perceive pain, and analgesia means no pain. Pain doesn't exist while I'm narcotized or while I'm doing hypnosis. Cannot exist because my cortex is not perceiving that thing. There is something, yes, of course. The body is reacting to that. There is a reflex of the autonomous nervous system with all that inflammation release that we talk about. But that is not pain. This is another thing, okay? That is called surgical stress. That is the devil that we have to put in the jail. And in order to do so, we have to measure the autonomous nervous system. Okay? So why do anesthesiologists provide painkillers? Painkillers. Well, in fact, they provide painkillers because what they want to do is to promote the parasympathetic activity in order to have under control the sympathetic inflammation reaction. Okay? And to keep that balance that I showed you at the beginning. It's already proven that if you use ENI during your general anesthesia, you will be able to titrate your analgesics, not only your opioids. ENI can be used during opioid-free anesthesia, can be used with blocks, can be used in any circumstance. And when you titrate your analgesics, then you will be able to improve the outcomes of your patients because you will know and that detect the etiology of the hemodynamic event. So you will know if that hemodynamic event has to be treated with analgesics or not. And you will be able to predict the postoperative pain. And you will be able to diagnose, the hemodynamic reactivity. You will be able to detect it in advance, as we said. So we are going to be able to predict hemodynamic reactivity. This has been proven by several articles. There is one from Boselli, but this one is from Matthew Jan, is one of the first ones that was published. And it says that if you are, what I told you, with a ENI value lower than 49, then the probabilities of having an hemodynamic response increase very much until you arrive to 30. And it will happen in the next 5 minutes. So you have 5 minutes to react and to add the right drug in order to avoid to have that hemodynamic reaction. One of the examples that I normally do is if you have two anesthesiologists in the OR and one is looking at the ENI and the other one is looking at the hemodynamic screen, you will see that the one looking at the ENI is doing things, is administering this drug, is decreasing the etc., while in the hemodynamic monitor, everything will be very stable. The other one will not be doing anything. And you know what happened? A lot of times I've been in the OR, and the doctors, when the ENI reacts and the hemodynamic monitor doesn't, they said, well, but if I treat that reaction of the ENI monitor, I'm treating the monitor, I'm not treating the patient, which is laughing. What happens is that they trust much more on the hemodynamic monitor than the ENI. Why? Because they have been doing anesthesia with the hemodynamic monitor for ages, while the ENI is the first time that they have it in there, right? But the ENI is much more precise and much more sensitivity, as we saw in the Funke study, and it's faster, as we can see here. So we will be able to prevent those hemodynamic responses much better if we follow ENI and not hemodynamic. Hemodynamic monitors should be a forget in order to titrate analgesia because the relationship with nociception is just flipping a coin. And you see it here, okay? But we have to convince them. This is the change of paradigm that I told you. People has to put their fingers in the wound, okay? They have to see it. So this other study is proving as well that we are able to diagnose the etiology of the hemodynamic event. Doctors, when they are in the OR and they see that they have an increase in blood pressure, they don't know if they have to increase, well, before the ABS monitor of the set line, they didn't even know that if they have to increase the propofol or the sevoflurane. Now they know it. So now the question is, should I increase my analgesia or should I put a vasodilatator? And normally, you know how they solve it. They just give an extra bolus of fentanyl. And if it's solved, it's fine. And if not, they said, well, I was wrong. I will go for nicardipine or rapidil. But the patient had already an extra dosage of fentanyl, right? So this study was done in order to prove that ENI is able to detect that. So what we did was an observational study, and we said, well, the protocol is going to be the following. If the if the hemodynamics increase at 20%, then you will give a bolus of analgesic, of fentanyl. And if the blood pressure goes down, then obviously the reason why it went up, it was because of nociception. And if it doesn't, if it stays high, the blood pressure, obviously I have to add a vasodilatator because the etiology, the cause why the blood pressure was high was not nociception, was hemodynamics. So they did that and they observed what happened with the ENI. And they realized that with a high blood pressure, when those patients were reacting to the sulfentanyl bolus, decreasing the blood pressure, the ENI was already low. and was telling to the doctor that yes, you have to add some sulfentanyl. And probably it was lower 5 minutes before. So we could have already add that sulfentanyl before that hemodynamic reaction. And those 5 minutes, the patient was already releasing inflammation, which is the reason why it caused pain later on. There were other patients in which the blood pressure was high and didn't respond to sulfentanyl, so they had to add nicardipine. Those patients already had high ENI, telling you you have a high parasympathetic, so telling you you are not in pain. You have to go other way. You have to go to nicardipine. So ENI is able to differentiate when you have to add fentanyl or when you have to add urapidil. Okay, if you have a high ENI and a high blood pressure, go for urapidil. Don't go for fentanyl.